dado una disculpa, en la agenda no tenía las 10 de la mañana y estaba yo haciendo hasta tiempo en la oficina para llegar acá, así es que me disculpo por un error administrativo. Pero bueno, ya después de esto quisiera darles la bienvenida en este workshop. Estaba yo leyendo, fue cuando me di cuenta que eran las 9:30, porque empecé a leer el programa y decía sobre como la manifestación macroscópica de la mecánica cuántica, ¿no? Y tenía ahí una pequeña descripción. Y bueno, yo también me dedico a eso de alguna forma. Yo hago estado sólido y no es otra cosa también más que la manifestación macroscópica de la mecánica cuántica. Y pues me da mucho gusto, ¿no?, que estén aquí, que tengan este workshop. Welcome, benvenuti, buongiorno. Y pues de verdad les deseo que sea muy fructífero. Otra vez una disculpa, realmente me apena mucho. Se ve poco profesional esto, pero bueno. Y pues gracias Jorge y a todos ustedes, a todo el Departamento de Cuántica y Fotónica, de Física Cuántica y Fotónica, por hacer este workshop y que tengan una feliz jornada. ¿Sí? Bueno, gracias a ustedes.
Bueno, pues muchas gracias a la doctora Nogués por aceptar venir a la inauguración del evento. Entonces, como ella ya lo dijo, el tema del workshop es presentar resultados novedosos en el estudio de fenómenos cuánticos que se manifiestan a escala macroscópica. Y básicamente la idea de este tipo de fenómenos es que un número muy grande de partículas ocupa un único estado cuántico individual, y entonces por ese motivo las propiedades macroscópicas aparecen a escala macroscópica. Entonces en este workshop lo que hemos buscado es presentar resultados novedosos en esta área desde diferentes perspectivas. Por un lado, uno puede tener sistemas cuánticos macroscópicos hechos de materia, de átomos, o hechos de luz, o de bosones, o de fermiones, o de sistemas que no interactúan, o de sistemas que interactúan muy fuertemente. Y cada uno de estos aspectos, aunque tenga cada una de estas diferentes sistemas, aunque sean muy distintos y muy diferentes en su descripción, comparten esta idea de un único estado macroscópico que describe a todo el sistema. Entonces, vamos a dar inicio al workshop, pero antes de eso quisiera hacer algunos agradecimientos. Por supuesto quiero agradecerle a la directora Cecilia Nogués por darnos la oportunidad y el espacio de organizar el workshop, a toda la administración del instituto que nos ayudó muchísimo con la organización y la difusión del evento. Quiero particularmente agradecer también a mi equipo, a mis estudiantes, al doctor Jackson Poveda, que también han estado trabajando muchísimo ayudándonos a la organización, y por supuesto agradecerle a todos los invitados que aceptaron venir a dar una conferencia. And at this point I will switch to English because at least the first conference will be in English. Okay, and I would like to start presenting Dr. Patrícia Castilho. So, Doctora Castilho, well, I met her many years ago in Brazil when I was doing my PhD there. She was just an undergraduate student, and since then we started to work together, setting a new experiment on Bose-Einstein condensates. And now, well, later she finished her undergraduate thesis. Then she moved to the master in the same place in Brazil at the Instituto of Physics of São Carlos, University of Sao Paulo. She got her master degree and her PhD degree there. Her PhD degree she made a sort of cooperation with Italy in in the University of Florence, and Laboratorio Europeo de Espectroscopía No Lineal, where she made some measurements. And since July, right, she is a full professor at the University of Sao Paulo, and she's setting a new experiment in probably 2D physics of quantum macroscopic systems. And today she will be presenting a talk concerning what she did during her postdoctoral internship in France concerning two-dimensional Bose gases. So, okay, Patty.
Hello?
No? Okay.
Hello? Hello? No? Hello? 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 See? What? Oh, sorry. Okay. I think it's working. Yes?
Yes.
Okay. Let me just. Yes. So it's a great pleasure to be here and finally visiting Jorge's lab. So as he told you now, we met many years ago, about 13 years ago, so really a long time. So I'm really glad to be here, and I would like to thank you for this nice introduction, and thank also the organizers for putting together this workshop, that I'm sure it will be a very nice event. So what I want to talk to you today is about part of the work I did during my postdoc in France in the group of Professor Jàidar, in which I work with uniform 2D Bose gases. And here I want explicitly to tell you about the dynamic symmetries of such systems. Okay? So systems that exhibit symmetries are interesting because symmetries are always behind conserved quantities of these systems. So if we have a system which has a spatial symmetry that is associated with the translation and the rotation of the system, we have that both the linear and the angular momentum are conserved. So these are the usual symmetries we learn in basic courses of physics, but there are also another class of symmetries which we call dynamical symmetries that will involve transformations of the systems in both space and time parameters. Okay? And this transformation will leave the action of the system or the equations of motion of the system invariant. So we can give one example of a simple system that shows both class of symmetries, which is the Kepler problem. So if we have two rigid bodies that orbit one around the other, as the Sun and the Earth, and this movement is governed by this equation of motion, in which the force acting in these two bodies is simply the gravitational force, we can see that these kind of systems have a rotational invariance, which leads to the conservation of angular momentum, but it has also what we usually call hidden symmetry, that is the conservation of the Laplace-Hunge-Lenz vector, which means that these orbits are closed and the energy of the system is always smaller than zero. And this hidden symmetry constitutes a dynamical continuous symmetry of the problem. Okay? So now, if you have a system that has a dynamical symmetry, there is a special class of these systems in which they have this scale invariant property. This scale invariant is pretty much when the system, the equations of motion of the systems are invariant under a dilation transformation in space and time, which are given by this set of two relations here. So if, for example, you have a collection of non-relativistic particles that do not interact, you can show that if you apply this kind of transformation, the kinetic energy of the system will rescale with this lambda parameter square, and the action of the system, which is proportional to the integral of the kinetic energy over time, is left invariant. Okay? So now if this system interacts, and the interaction energy is also rescaled with the same scaling parameter, then this system is said to be scale invariant. And such systems, they are interesting because they have very simple thermodynamic properties. For example, the equation of motion of these systems, the equation of state, sorry, of these systems, depend only on the ratio of the chemical potential over temperature and not on these individual two parameters. So this simplifies a lot the thermodynamic description. So the examples we have, some examples we have on scale invariant systems are this collection of non-relativistic particles, either that are not interacting or that have interactions described by 1 over r squared potential. Also, the 3D Fermi gas at unitary regime is also a scale invariant system. And finally, the weakly interacting two-dimensional Bose gas also show this property. So here what I'm showing you is the equation of state measured for a weakly interacting 2D Bose gas in the group of Shenxin. And even for different, so here in this inset, I show you the density profile of different clouds at different temperatures with different chemical potential. So they look very different, but once you calculate the rescale equation of state, you see that you reach a universal behavior in which all the curves overlap into a single curve. Okay? So in this work, what we want to do is to go beyond these static properties of these scale invariant systems and look the dynamics of a 2D Bose gas in a harmonic potential. So all the results I will show you have been recently published on PRX. So if you want to take a look afterwards, you can just follow this reference. Okay, so here I come to the outlook of my talk. So I divided in two big parts. So in the first part, I will show you the results I just introduced you before. So I start first describing the experimental setup. Then I enter on the dynamical symmetries that these systems are related to. And I show you 3 experiments we perform in order to show to prove the dynamical symmetry we associate with such systems. And in the end, I finish discussing a bit the observation of two-dimensional breathers. And on the second part, I want just to introduce to you the Brazilian group I have recently joined as a permanent member, just to give you a flavor of what has been done in Brazil these past years. Okay? So the experimental setup is quite simple. We want to produce a uniform two-dimensional Bose gas of rubidium-87 atoms, and in order to do so, we use the usual steps for cooling and trapping rubidium atoms until we reach a Bose-Einstein condensate in 3D, made in a crossed dipole trap. So here there is a problem. Okay, it's not appearing all the image here, but this is supposed to represent this 3D BC, and here it should have a glass viewport up and down, but it's not a big deal. Okay. So then once we get this BC, what we do is that we load these atoms into a vertical optical lattice with tunable confinement along the vertical direction that goes from 2 to 5 kilohertz. Later, we switch on the in-plane confinement using a digital micrometer device that is drawn here in order to create a box potential and produce clouds with uniform density. So this digital micrometer device is nothing more than a set of array of micromirrors that are controlled individual to two positions, on and off, such that you can shine light to the direction of the atoms, or not, you can shine to another place. And you can draw anything you want with these micromirrors, such that the atoms will accumulate in the dark regions of this DMD. So now, if I cool the atoms down to the degenerate regime, and I perform an absorption image, what I see is this image here, in which I produce a uniform cloud with the shape I put on my DMD. Okay? So as I told you, we can do many, many different shapes. So here I show you some other shapes we have produced in the lab. So these are all absorption images of the atomic cloud. And this shows you the large flexibility of this kind of two-dimensional potentials. Okay? But in all experiments I will talk to you today, what we do is once we evaporate the cloud into the degenerate regime, we switch off this box potential and we let the atoms evolve in a 2D harmonic potential produced by a pair of coils in anti-Helmholtz configuration. And the frequency of this harmonic trap is of about 20 Hz. And we let the atoms evolve for variable times in order to later take an absorption image and study the dynamics of this cloud in this harmonic potential. Okay, so now before entering on the dynamical symmetries that we have associated with these systems, we need to know how to describe these two-dimensional clouds. So as I just explained, these 2D clouds are produced from 3D gases that are strongly confined in one direction of space. So usually this confinement is made with a harmonic potential, so we use an optical lattice. And if h bar times the frequency of this strong confined direction is much larger than the thermal energy of your system, you enter in the quasi-2D regime, in which the scattering properties of your system are modified by the strong confinement. So it appears here this LZ term that is the oscillator length of this strong confined direction. Okay? So now if we are dealing with weakly interacting atoms, such that the scattering length is much smaller than the oscillator length LZ, the interactions are mediated by a dimensionless parameter, G tilde, that is given by this relation here, such that we can describe the interactions of the atoms as a mean field approximation. Okay? So in this case, the description of the gas can be done by means of a classical field that evolves according to a Gross-Pitaevsky equation that is written here in this form. It's also in this context that, so I don't know if all of you are familiar, but Bose-Einstein condensation do not happen in a purely 2D system, but you have a transition to a superfluid state, and it is in this context that this transition happens via a BKT phase transition, which occurs for a critical phase density given by this relation here that will depend on the G tilde parameter I just defined. Okay. So now that we know how to describe this kind of systems, we can try to look for the symmetries that are involved on this problem. So I will start first with the free cloud, such that the external potential is set to 0, and we have a simpler Gross-Pitaevsky equation here without any external potential. So in this case, we can see that the transformations that leave the equation of motion, the Gross-Pitaevsky equation invariant, are given by a time translation, given with this relation here. Also, we can look for the dilation transformation I told you on the introduction that will modify space and time with these two relations, such that the wave function is modified by this relation here, and the kinetic energy will keep its scaling with the lambda square parameter. And now, if we look to the interaction energy of these 2D gases, defined as this equation, we see that also this interaction rescales in the same form. And yes, the system is really a scale invariant system. Okay? And there is also another set of transformation that we call expansion, that will change both time and space in such a way. And if we combine these three sets of transformations with the usual Galilean transformation of space, we found a general formula for all transformations that leave the Gross-Tversky equation here invariant. Okay? So now, once we know we have this general formula, we can ask ourselves which is the symmetry group, if there is a symmetry group that is associated with these transformations. And in order to do so, what we do is we look to the infinitesimal generator for all these possible transformations, and we find these three generators here, LA, LB, and LC. And after some linear combination of the three, we can define L1, L2, and L3 that show this commutation algebra I'm written here. Okay? And this algebra is the same of the Lorentz group SO21 symmetry group. So we can associate the properties of this group to our system. So I didn't do all this calculation here, it's quite long, but if you are interested, you can take a look on these three papers here. So the two first are for two-dimensional systems, and this last one is 3D Fermi gases. Okay? So good. So now we know how is the symmetry for the free cloud. Now I told you I want to study the dynamics of the system in a harmonic trap. So if I look for the case in which I add a harmonic potential to this Gross-Tversky equation, I can first take a look on the dilation transformation I just told you before, and we see that even though the kinetic and the interaction energy rescale in the same way, the potential energy rescales now in a different way. So the system actually is no longer scale invariant once we put this system into a harmonic trap. However, there are a set of transformations that leave this Gross-Tversky invariant, and we can show also that these transformations can be associated with the same symmetry group SO21, and we can use again the properties of this group to describe our system. So this you can take a look on, So this you can take a look on the supplementary material on our paper. We do all the calculations in order to prove that even in a harmonic trap we have the same algebra. And this algebra is very interesting because it has a very strong consequence on the evolution of the potential energy. So the potential energy will oscillate in time with 2 times the frequency of the harmonic confinement. Okay? And this has been observed already on these 2 papers I list here. And we also observed this on our experiment. So what we do, we start with a uniform field square, like this, and we let this square evolve. So we prepare it in the box potential, we switch off the box potential, and we let it evolve in the harmonic trap only, in 2D. Okay? And what we see is this set of images I'm showing you here, and we can calculate the potential energy with this expression here directly by numerically integrating the density profile. And we obtain this graph that we clearly see this oscillating behavior of the potential energy, and once we fit these experimental points, we get a frequency of 38.5 Hz, while the trapping frequency is of 19.3, so it's in very good agreement with what we expect. So now there is another thing I can point out from this data, So even though the potential energy oscillates in time, we see that the shape has very different shapes up here. And if I look only for the images in which I have the same potential energy, I see that I have no restrictions on the shape of the cloud. I cannot really predict what will be the shape of the cloud I will observe for each potential energy, even though they have the same potential energy. Okay? So I will go back to this at the end of this presentation when I discuss the two-dimensional breathers. It's just for you to keep it in mind. Okay. So now that we know which is the symmetry group associated with these systems, we can use the symmetry group to link two different solutions of the Gross-Dostoevsky equation and map their behavior. So this can be done, for example, keeping the interaction energy of these two wave functions, PC1 and PC2, the same, and also making this cloud evolve in the same harmonic trap. So if we do this, and we use all the algebra we knew from the SO2 symmetry group, we can have a general formula for the rescaling of time, that is going to be here on this eta parameter, and the rescale on position, okay? Such that if I have a PC1 that is a solution of this full Gross-Dostoevsky equation, this PC1 will be mapped into a PC2 that will be rescaled by these two relations here by this rescaling function f, the r and t, okay? So in the experiment we can simplify a bit. So what we have is that we have special conditions for this mapping of r, t into r prime and t prime, and we want to map t equals 0 into t prime equals 0, so the same initial time. And we also start with a cloud initially at rest. So we prepare it in the box potential and we switch off, and this cloud is at rest, and then it starts to evolve in the harmonic trap, which makes the derivative of this lambda parameter at the initial time equals to 0. And this simplifies this relation here for alpha, delta, beta, and gamma, such that beta, gamma, and gamma are equal to 0, and delta is equal to 1 over alpha. If we use this simplification, we change this general formula, like these new relations I put here in orange, and we can use them to try to map the evolutions in the experiment. Another thing we can do, we can go a bit further and try to connect the evolution on two different harmonic traps. So we can do this by adding a new parameter, zeta, which will rescale these trapping frequencies. And then with this, we can see that changing on the change on the harmonic frequency is just a dilation transformation in which the position is rescaled like this and the time is rescaled like this. So if I add the dependency of this zeta parameter into this general formula, I get this final set of equations in which I put the zeta parameter here in orange for you to compare with this previous formula I showed you. And this we can try to see on the experiment. So this is what we do now. So we want to link the evolution of two wave functions at different trapping frequencies. So we start with the same cloud, a uniform field triangle with side equal to 40 micrometers. And here we have 4 × 10⁴ atoms in these two clouds. And we want to compare the evolution with omega 1 equals to 0, which means that the cloud evolved freely in the 2D plane, with the evolution in the harmonic trap with frequency of about 20 Hz. So if I do this, okay, so with this set of parameters, actually the rescaling in position, in size, is the same. So the alpha parameter is 1, and since I want to rescale a free evolution in 2D into this harmonic trap, this zeta parameter tends to infinity from the previous relation I put it here. Okay? So this zeta parameter tends to infinity, which modify a bit the scaling relations I had before. So I have this final two relations here that I can try to observe in the experiment. So if I let the cloud evolve in these two different harmonic potentials, I observe this sequence of images, and we can try to see this scaling relation pretty much calculating the overlap between these two density profiles. Okay? So how we do it, it's a bit complicated. So we define this P parameter in which I choose one image of the first set of evolution and I calculate it for all the images in the second set, changing this lambda parameter that will rescale the first density profile in this form. Okay? So here I have for each combination of images, N1 and N2 and 2 and 2, so I have many values of lambda in order to get later the maximum of this P parameter with respect to the lambda I'm using. So this I define as the overlap between the density profile N1 at T and N2 at T prime. And actually, in order to see these scaling relations, I want to see the optimum value of this overlap. So the maximum value of this overlap with respect to T prime, to see which is the image that matches better the shape that for the image I choose on the first set of images. Okay? So then I define this lambda T as being the value lambda from the maximum value of this overlap with respect to T prime. And if we now plot these things, what we see is that this is omega times T prime, and here is omega times T, that is the first scaling relation I have here. Okay, and these are the experimental points, the circles, and the solid curve is this equation with no free parameters. So the theory matches very well our data, and this is also the case when we look for the lambda parameter here. That is the second one. Okay? So we can clearly describe and map the evolution of these two wave functions done at two different harmonic potentials. Okay. So now the question is, can we go further? So far what I can do is change the harmonic potential and change the size of the system. Is the two things I can do. But can we go further? Can we, for example, map the evolution of two wave functions with different interaction energies? And the answer is yes, we can, if we go to the hydrodynamic regime. So if we write the Gross-Dostoevsky equation now in terms of the density and the velocity fields, which is the hydrodynamic equations, we can use the condition that the healing length of the system is much smaller than the size of the system, such that we can neglect this last term, which is associated with the quantum pressure. And by doing this, we can find a relation to map the two wave functions with different interaction energy. So I introduce another parameter here, mu, that will rescale the interaction energy here, and with this new parameter we get this set of equations for rescaling time, position, and the atomic density. So here I put the mu parameter in orange to show you that these relations are very similar to the ones we used before, but with this additional parameter mu. And instead of looking only to the wave function of the system, we have to rescale it using the interaction parameter G tilde also. Okay? So in our system we perform two experiments, which we present on the paper, but here I will focus only on the second one, in which we change both the interaction energy and the size of the system. So what we do is we start with a uniform field square with different sizes. So the first one has a size of 27 micrometers, the second one has a size of 37 micrometers, and different atom numbers. And we let it evolve in the same harmonic potential in order to observe this series of images. So now, if we look by eye, you can see that these two images that look more similar between each other, they are dislocated in time, as we also expected to be, since we have to rescale both the position and the time. Okay? So in order to analyze this data, we do the same method of calculating the overlap, and what we obtain are this set of graphs here, in which I show the rescale in time in the first graph, and the rescale in a size in the second graph. And this, again, the solid lines are the theory, so the relations I showed you in the previous slide. So these relations here, with no free parameters, and we see that they match quite well the experimental points. And this, so once we are in the hydrodynamic regime, actually what we observe is a universal behavior of the cloud in which we can change any parameter, the atom number, the size, the interaction parameter, the harmonic confinement in which this cloud evolves, and all these changes can be mapped into a universal behavior. So this is quite nice. Okay, so now I enter to the last part of this first part of the presentation, in which I discuss a bit the two-dimensional breathers we observed. So far what we did is we could link the evolution of two different wave functions, PC1 and PC2, given the fact that we vary all parameters, and the interaction energy we can vary only on the hydrodynamic region. We also saw that the potential energy has this periodic evolution with frequency of given by 2 times the frequency of the harmonic confinement, but there were no constraints on the evolution of the shape of the wave function. So if you remember what I showed you before, we started from a uniform square, field square, and we see that it evolved like this set of images here, and we see that this evolution is not periodic. So the shape of the cloud is not periodic, which means that the wave function describing this cloud do not evolve periodically either. So, but is it true for all shapes? So what we did is we tried with a triangle, an equilateral triangle, and we look how it evolved in time. So is there a period we can relate to the evolution of the shape of the cloud? So we can take a look on this GIF, and we clearly see that we starting with a triangle that points downwards, I think. Yes, it goes upwards and downwards and upwards and downwards. So it's really periodic, the motion of the atoms, when we start with an equilateral triangle. Okay, so I just show you here the first images of that GIF I showed you before, and here we can also calculate the overlap of each image with the first one in order to see if we see an oscillatory behavior. And indeed, we see oscillatory behavior that goes down, which means that the triangle that was pointing up downwards points upwards, and then it goes up again, showing that the triangle points downwards again. And it's quite uniform, as we can see already by the images. Okay? So this behavior is what we call a breather. So this is what we call a two-dimensional breather, and it's a wave function C that evolves periodically according to the Gross-Plotniewski equation. So there are other breathers that we can list here. So the simple case of a breather is the steady state of the system. But in 1D, for example, if you go for parameters smaller than 1, a bright soliton is a breather that evolves periodically in time in this kind of systems. And here you have a reveal on this kind of bright solid tones in 1D systems. Okay, so then we did also a set of numerical simulations in order to see if it was true that after T/2 we recover a uniform field triangle, and these are the images we see from the numerical simulations, and we calculate here again the overlap of the first one with the following ones. And here I showed you this overlap. So I showed you the difference of this overlap with respect to 1, which would be a perfect overlap. And we see that it's very small. And as we approach the hydrodynamic regime, this value decreases even further. So yes, we see also the same kind of behavior on the numerical simulations. But actually, we cannot explain it, why it happens. And we tried many different shapes. So I don't have all the gifts here, but we tried the square, the pentagon, the hexagon, a star, a right angle triangle, and we see no periodic evolution of the shape of the cloud. We see for the triangle, and maybe for the disk cloud, a circle, which period that is equal to 2 times the period of the harmonic trap. And this result is not completely clear on the experiments, but it's quite robust with the numerical simulations. So here we have many open questions. So since we cannot explain this behavior analytically, we have these many questions. So the first one is why we get a different period for the triangle and the disk. And also, is there a way of proving this breather mathematically? Can we do it analytically or not? And are these breathers linked to the dynamical symmetries I just showed you before? In this case, if they are linked, there will be also breathers for interactions described by 1 over r square potential, and also for 3D gases, Fermi gases in the unitary regime, that we don't know which will be the shape, but they will be there. And are these breathers resilient to an increase of this G tilde parameter? So we will see some effects of quantum anomaly that is due to the fact that actually we are only in the weakly interacting regime, and we have a logarithmic term on the interactions, on the atomic interactions, once we departure the weakly interacting regime, increasing G tilde. So all of these are open questions for these 2-dimensional breathers that we could not yet answer. So so this is always a team work. So here is the team of the rubidium team, and most of the work was done by this guy here, Rafael. So he just finished his PhD now in September, and his thesis is very complete on this subject. He do all the math. So if you want to take a look, I think soon it will be online, and you can look. It's really good. Okay, so now I go to the second part, that it's a bit more relaxed. So I just want you to give a flavor of what the Brazilian group, I did my undergrad students and PhD, and also Jorge and Fred did their PhD. And now I'm back there as a professor, so I want to give you the idea of what they do there, and yeah. So I'm back to Brazil, so in the University of Sao Paulo, in the Physics Institute of São Carlos, which is a city in the countryside of São Paulo state. So here there are 2 pictures of the campus of the university, which is quite nice, quite sunny. And this is the atomic physics group, so we are part of a bigger group, the CEPOF. So here is the link to our website. And the atomic physics part of this group has 3 professors. So Professor Banhato, that is the group leader of all the CEPOF actually, and he has 2 experiments. One, a rubidium BC experiment, in which He performed some studies on thermodynamics in collaboration with Victor Romero here, and also on quantum turbulence. There is also a second experiment on mixture BC with sodium and potassium, in which they want to study miscibility effects and couple vortex lattices in such a mixture. So the second professor is Philippe Courtet. He works with strontium atoms and he has 2 labs, both working with light and matter interaction in a cold cloud or with atoms in a cavity, in a high-finesse cavity. And there is also Professor Emmanuel Hein that is building up an experiment with dysprosium atoms. So it's in the early stage of the experimental setup. And now I have recently joined this group. So, and the idea is to try to implement a 2-dimensional system with potassium atoms, such that we can tune the interactions, which is a new ingredient to all the physics I discussed to you today. And at the beginning, I will be involved in these 2 experiments as well, as a collaborator with Professor Bagnato, that was also my PhD advisor. So we already collaborated before. Okay, and to finish, I just want to say that we are organizing a school on April, and in which we are going to talk about many important aspects on the field. And there is a very long list of speakers with very important people as Bill Phillips, Randall Hewlett, and Stringari, Kleppner. So if you want to try to apply for this school, do it, because we have grants also for bringing students. So yeah, it's a limited number of positions, but we have grants. So if you are interested and motivated, go to this website and do your subscription. Okay? So that's it. Thank you very much.
Thank you very much for your very interesting talk, Patricia. We have actually plenty of time for questions. So, Victor? Okay, después de
Just a simple question or comment. Because you find this triangular symmetry, and I can figure out that the pentagonal and the star, you break a lot of symmetries and you cannot have in 2-dimensional. But the square one, I don't understand why you don't have this.
We don't have.
Do you have some idea, something? Because the pentagonal and etc., of course, no, in this 2-dimensional, or you don't have it. That symmetry. But the square is.
Yeah. Oh.
You don't have any.
No, we have no idea why the triangle is so particular, and we observe this clearly periodic evolution. This we really have no idea. No idea. We try to find some explanation, but analytical one, but we didn't manage. So that's why we did the numerical simulations, because we thought at the beginning it was an artifact of the experiment. But no, doing the numerical simulations, we don't see this behavior for any of the other shapes. We only see the behavior for a triangle with this period equals to t/2. And for a uniform disk, we see, but with a different period. But it's not clear on the experiment.
Because you can push, for example, with this extra term that you have the Gross-Pitayevsky equation. You have the R squared, no?
Yes.
And probably you can break the symmetry there, or to induce some kind of symmetry and try to.
Yeah, so
I don't know if you try it or something.
Even with the harmonic potential, so we have a symmetry, a well-defined symmetry for the system, which is this SO21 Lorentz group for the symmetries. And but these do not explain. So these do not put any constraint on the shape of the wave function. These do not.
Okay.
So the only constraint that it input is on the evolution of the potential energy, and then you can relate different wave functions into one another. This you can do with the use of symmetry, but if you don't have a first evolution, you don't know how it will evolve. So you need at least one to know the shape, and then you can construct any other evolution that you want, and you know how it will behave. But if you don't have a first one, you don't know how the shape will behave. There is no analytical prediction, no analytical restriction that will say, okay, from a square it will evolve like this. No. And neither for the triangle.
Thank you.
I think you essentially answered my question, but still just a little bit more in the you put in the last questions there. You said that the first one, square, pentagon, etc., they are not periodic up to 5t. That's the experiment.
On the experiment.
And you can to solve the Gross-Piaget's equation.
Yeah.
And
So we did
you can go
numerical.
higher than 5t.
Yes, we did. So on the simulations we did.
You
So we did numerical.
see it.
Yeah, no, we
Okay.
never see.
Yes.
So we did a numerical simulations for all the shapes we tried. So I think we tried even more here, at least some, but we tried some exotic shapes also, and that were kind of symmetric, just to see if we found something else. And the numerical simulations, we did it for very long times, and we didn't see any periodicity instead of the triangle and the disk.
There's just one small detail, probably. I don't know how large. But you see, evolving these types of equations for a very, very long time, it is very dangerous because there are numerical errors.
Yes.
That you have to make sure first that the evolution remains unitary, and that's probably the stamps are too large or not. That's also something that should be checked.
Yeah.
I believe that
So it
just a
was
small
Jean
warning.
himself, Dynamical himself, that did the simulations.
Okay, you have
So,
to-
and I think he checked everything.
checked
We
everything.
discussed.
So there is nothing for a very long time.
No,
Okay.
for a very long time.
Experimentally and with
No.
hospital.
Yeah, experimentally we cannot go much further
Much
than
than
5
yes, I can understand.
But yeah, but
Numerically-
numerically we went further and we didn't. And
Rosario?
Patrícia, I have two questions. The first one is, you mentioned within the open question that you should include this term that is going like 1 over r squared. Why do you need to include that term?
what do you?
There, interaction
Here?
with 1 over.
This?
Yes.
So this actually is, if we want to try to search for these bridges in other systems, so we can expect to have, since these two systems are also scaling invariant, so both of them, they will respect the same symmetry, so they will be described by the same symmetry group. And if we see a breacher in our system, maybe in these two systems there will also be a kind of breacher. We don't know if it will be a 3D square, 3D triangle for the unitary Fermi gas, for example, or if it will be another shape. But if it's linked to the dynamical symmetry, there will be breachers in these two cases for a collection of particles with interactions described by 1 over r squared, and also for the 3D unitary Fermi gas, if it's linked to the symmetry, to the dynamical symmetry.
Another question, or perhaps a comment. This relationship that made by Petrov, in which you have the effective coupling interaction in 2 dimensions, was derived, as far as I remember, taking into account the geometry of the space in which the collisions occur. So, if the collisions occur in these pentagon or hexagonal geometries, why do you expect that you have to keep the same effective complete interaction?
Okay. So I think what he says about the geometry of the collisions is actually that even if you are in 2D with the system, then the collisions happen in 3D. So actually, it's the condition for the weakly interacting regime. So the scattering length of your atoms is much smaller than the oscillator length of your strong confinement. So actually these interactions, they do not happen in 2D. So it's not a 2D process, but it's still a 3D process with an atom that is strong confined in one direction. And this modifies a bit the scattering properties. These don't, from what I know, these do not put any constraint on the shape of the 2D cloud in the 2D space. So you can have a harmonic potential, you can have a uniform potential in any shape you want, and these do not change this effective interaction. If we depart to the weakly interacting regime, yes. So we have the other term on the scattering amplitude that will give us this quantum anomaly effect that was observed in experiments.
Any other question?
Thank you for the talk. It was very interesting. My question, I have two questions. The first one is, what do you expect when you increase the interactions from a weakly interacting regime to a more strongly regime? And the second one is about maybe if there is no periodicity for the square, pentagon, etc., is there a kind of quasi-periodicity so that the shape doesn't return to the same shape but like an exponential in the correlation function or...
So we didn't explore it too much into detail, but we can see that, for example, if we start with a square, it evolves and we see this diamond shape here, and then it looks like it tends to go to a square, but it's never anymore uniform, never. So if we look for the triangle instead, what you have is that it's uniform. So it really recovers the initial shape that you have on your cloud. Okay? So in the case of the square, you always have some edge effects and it's never anymore uniform. We didn't see it. But we didn't study correlation functions on this set of data. It could be interesting to study this. And about the other question, actually we don't know what we expect when we increase the G-tilde parameter, because all the formalism I used to describe this 2D gas is no longer valid. So we cannot use anymore a classical field to describe this system. It's true that you will start to see corrections, especially on the interaction parameter G-tilde, so it will appear a correction with a logarithm dependence. But then actually we don't know if we go so much to very high G-tilde, we don't know what we expect. Even the superfluid transition is an open question. We don't know if it will occur and how it occurs, because the BKT formalism is no longer valid once we increase this interaction parameter. So we don't know what to expect.
Okay, any more questions? No? Okay, I have one. A very not smart one, but what happens if you don't use a equilateral triangle?
If it's not equilateral?
Yes.
It doesn't work. So we use a right square.
Okay.
And it doesn't work.
Okay, so it's
the equilateral triangle.
That's it.
Yeah.
Okay.
It's a very... And we tried the idea to try the hexagon is that it's two triangles, but it's not periodic. So it's super weird. We really don't understand why, but very robust in the numerics as well. So we believe it's true. We really see something that evolves periodically in time, and but we cannot explain.
Wow. Any other question?
Yeah.
Okay, Andres.
It is not clear to me, what do you see when you use the disk? Because you say it's probably periodic, but what exactly do you observe?
Can I just put it here, George?
Yes.
Yes. So we have, so I have the set of images for the evolution of the disk, but pretty much what we will have is that it's no longer uniform. So if you look for the disk, so this is the experiment for the disk. If it opens, yes. Slow Windows computer. No? Oh, I hate this Windows. It's a mess.
Se você provar outro...
Posso abrir com Paint? Wait.
Haces preguntas muy difíciles, Andrés.
No, I was not prepared to show you. But so what we see is pretty much that it is never uniform. So in the numerics, it looks like it recovers a uniform shape, a uniform density after 2 periods. But in the experiment, it's never clear if we see it recovering the disk shape uniform. So we always have some edge effects or more atoms in the center, a higher density in the center, and it's never uniform. So it's not exactly the same wave function that we start with. So you see?
Yes.
But it looks a bit here, maybe at this time, maybe at this time. Here it looks like it is a bit uniform. But it's never, if we calculate the overlap as we did before, we have a much lower value for the overlap. So all the images I showed you, the overlaps were reaching 1, it was really close to 1. And here it's not the case, even though we can get mistake by looking to the images, you see. But here there is also always a kind of shadow in the edges. So we don't really, so this looks very uniform, but if we calculate in the end, it's never the case. And this is more or less the same with the numerics. So the numerics is a bit more clear. We see this kind of two...
those images, if you look at the diagonals, they are...
Yes, so it should be the diagonal. You see that it's in bold here. It's in bold, and here it should be something like here. This guy, and this guy. So it's a bit shifted, the images. So it should be, this is the 2 times the period. That should be the one we see on the numerics. But if we calculate the overlap from the experimental data, it's not clear. Even though it looks quite nice by eye. So it's, yeah. Okay.
Okay. So if there are not any more questions, we can say thank you to Patricia